Alrighty. Okay, so where are we here? This should be a little bit of a shorter video, just a sort of supplemental. I wanted to talk about, excuse me, a piece of equipment that I use on occasion. It comes quite in handy. This thing here, it says ESR leakage. That's the label I gave it. It's really probably best described strictly as a leakage test. Very low, very, how would you say it? Well, for example, this is a microammeter, that little U. Now it's shunted. I calibrated it. This circuit that's in this, it's inside the box. I just built it dead bug style, they call it, on a piece of copper. Actually, probably might even be able to see it. Yeah, there you go. You can see that mess in there. Anyway, that's what makes it go. It's based on, I was for a time a Patreon member, Mr. Carlson's lab. He has his own, this is his circuit basically for this leakage tester for capacitors, very low current leakage tester, low voltage as well. So I slightly modified it and calibrated it so that it can, the circuit's, if I'm not mistaken, it's supposed to run at 27 volts ideally. At 27 volts, the needler is over here at 100, right? And what should happen, especially on a properly functioning capacitor, is that you watch it drop. Eventually it comes to zero. And you know that you have a good non-leaky capacitor, okay? A couple of things that I don't recall Mr. Carlson ever mentioning, and I will mention about this particular device. There's two things with it. So, for example, these capacitors that I pulled out of this, these are only 16 volt capacitors. That's the rating. So, what I had found before it occurred to me what was going on, when I was, running a full 16 volts from, just look up here for a moment. You can see, there it is, that old Hewlett-Packard. It's showing only just shy of 5 milliamps, and it's set for just shy of 16 volts. All right, because this is a 16 volt cap, and when I was running this at 27 volts, blindly just plugging anything into it, the caps would misbehave in the sense that they would show as leaky. And then when I discovered, oh wait, it's because I'm exceeding the rating. So this I would say that I haven't tested, but I'm pretty sure you could do 10 volt caps. You turn your power supply down to 10 volts. The needle would be at a lower spot, but it still would be some indication. The other aspect of this, the neat thing that I've done in the past, when you want to compare, if you had a batch of capacitors that were all the same, you see, it's a function of, this whole thing it's a function of time. Okay, it's like just a capacitor. The best analogy, it's like a bucket. So you want to fill it. Electrons, water. Let's just use that analogy. So what determines how fast you fill it? That's just how much water you're putting into it, the flow rate, okay? So this one here is a 2200 microfarad. That's a fairly sizey capacitor. I've measured these in the past. They can take up to, I think, if I remember correctly, using a stopwatch, basically. I mean, it was almost 20 minutes to fill one from 100 to 0, because that's what's happening, right? That's the process. It's filling as you get closer and closer, right? And eventually it stops filling when it's full. Unlike a bucket of water, where the analogy breaks down is that this doesn't overflow and spill out the sides unless you really, the only way you do that is with pressure. If you exceed the voltage tremendously, you'll blow the thing up, I would imagine. As long as you're staying within within reason of the rating of the thing. That's basically what's happening. So you can compare and see how these things are behaving. Are they all taking roughly the same amount of time to come to full? And you use a secondary, like a stopwatch or your cell phone, to do it. And it's kind of neat because you can see the good capacitors are pretty consistent, not exact, but close enough. For the things, there's always that 10 to 20% tolerance rating on all this stuff. So anyway, so that's an interesting thing. If I could somehow build a timer into this, something that automatically stopped when the needle reached 0, or when current stopped flowing. I also added an LED, just for more fun. And that LED, you can, with low enough light, you can see it still on even when it looks like it's at 0, because there's still some. It's a special LED, that very low current LED that I've used for this, so it can be illuminated at a very low spot here, and then eventually, if the capacitor can do it, it'll go out. So it's kind of there's two ways to know that this thing is what's happening, right? It's crude, I guess, but I like it, and it works well enough. So what I was getting at was to show you what this is about. It shouldn't really, there's probably, I don't really fully understand the correlation between ESR and leakage. I mean, it's clearly Ohm's law. If this thing is, acting as a resistor and you put a voltage across it, then current will flow. So that makes sense. And that's probably the best way to model what's happening, essentially. Although the mode of leakage might be different, but there is still going to be, it's not a dead short. If it was a dead short, we have a different result, right? My power supply would be going off the rail. It would just be this Hewlett-Packard power supply, the one I just showed you, has this neat feature where you can determine at what point it kind of cuts out, has short circuit current, so you can kind of protect equipment and with that feature. But nonetheless, so this isn't a dead short, it's just a steady flow, right? Like a resistor would be. If we did some math and we said, well, 16 volts, and let's just round up and say 5 milliamps, you could figure out, what that resistor's value is. Ideally, a capacitor shouldn't be like this. So what I can tell you is that this has been sitting at, this is full. 40 is full at 16 volts. As I said, when you put it up to 27, it comes to 100. This is where it started, and it hasn't budged, and it's been on for well over half an hour, just sitting like this. And I imagine it would sit like this all day. And that's how you know you've got, even though it may read, here's the other thing that can throw people off and confuse matters. You could take I could use this device here to measure its capacitance. It's basically how big of a bucket it is, and it might show a correct amount. still and yet be quite leaky like this. So it's not always one thing to another like that. There can be different failure modes. They can all be connected. You can have a bad, you can, this can be reading way wrong for capacitance and be leaky. That can happen quite often. Lots of different things. So, yeah, that's, where are we here? We're just over 10 minutes. Just a very simple device, very handy. It can be, there's a switch here. I can use it for different types of capacitors other than electrolytic, such as like a polycapacitor, which has some different characteristics. The circuit is designed for this. So it's, I put the switch in. Most of the capacitors I ever deal with that are troublesome are of the electrolytic variety. So yeah. So there you go. Different way of testing them. Something you may have not encountered. I mean, you can do your standard this, and this can mislead you, just reading that alone. But ESR, I mean, it will show you something. It'll tell you that the ESR is high on this. That means it's acting like a resistor, and it shouldn't be doing that. That's not its intention or function ever. I mean, unless somebody tries to exploit that characteristic, but that would be an odd choice to make, I think. Yeah, and that's it. So this is just not really this. I'm getting into this radio. This is the ICOM 745. I'm looking at the regulator circuit right now, and so we're going to do some more in-depth stuff on that coming up next. So yeah, that's it for now. So I thank you again for watching. Please click like if you enjoyed that. Please subscribe if you want to stay in touch with new content, and hope all is well. Bye for now.